Okay, we want to get a linear model for this datum. Now, linear models of the form y equals bt plus a. So here's our matrix equation that corresponds to this model. You can verify that easily. We're going to find a, okay, this is an equation of the form ax equals b, vectors x and b, and we want to find the best x, which is an ab. Once we find that, we know what our best linear model is. Now, if I graph these 3 points, these 3 points won't lie in a straight line, but there's a straight line that comes pretty close to all 3. We want to find the straight line that comes closest, and having solved this for the AB that comes closest here, we get the equation of the line of best fit. So, our matrix A is a 3 by 2 matrix, and our matrix and our vector B is our 3 by 1 matrix. We define the transformation as usual, and all this is the same as before, except we have a smaller matrix, because before we were trying to do a quadratic model. Okay. Now, the transformation then that we define from R2 is from R2 to R3, defining the transformation of V, the transformed vector V as A multiplied by V. Okay? It's clear that this matrix acts on vectors in R2 because the lengths of the rows are 2, and maps to R3 because we have 3 rows, each one of which will give us a number in our AV column vector. Okay? Now, matrix A can easily be shown to have rank 2. If you row reduce this, you're going to get a 1, 0, 0, 1, and a 0, 0. So the rank is 2, rank meaning the dimension of the row space. So, the row space of A has dimension 2. The null space then has to have dimension 0, because in any case the row space is orthogonal to the null space. The dimension of the row space plus the dimension of the null space is the dimension of the whole space. Dimension of R2 is 2. Row of A has dimension 2, so row of A, the row space of A here, has dimension 2. Turns out that it's the whole space. The null space has dimension 0, so the null space consists of, it's a set consisting only of the 0 vector. Over here in R3, things are a little more interesting. The column space, being the image of the row space, has to have dimension 2, and also the row space of A transpose has the same dimension as the row space of A, because all you're doing is changing rows and columns, and the row and column space of any matrix have equal dimensions, and all that I don't want to repeat in all its detail. Okay, so, and then we have the null space of A transpose. Now, what's the dimension of this null space? This is of dimension 1. Now, this means that we can actually depict this space by some plane and some vector perpendicular to the plane. So this is the column space row of A transpose, has dimension 2. And what we're doing, again, is our B vector is not in the column space. That can be easily verified. So here's our B vector, and we have to project that B vector orthogonally into the column space, and actually we have to project it parallel to the normal vector, which will actually put it down here someplace. So here's our right angle. Okay, well, that's not a particularly good picture, but again, that's our context. Now, how do we do this? Well, we can do all our reasoning, but it comes down to, we just calculate A transpose times A and solve the resulting equation. Okay, so we're gonna actually do that. So here's our picture, same picture we've had before, a few details of the picture. But now we're gonna go ahead and just do the calculation.